My name is Teresa Nguyen, and I'm a senior at Westminster High School. My project is synthesizing hydrophobic carbon dots, HCDs, and testing HCDs as a respective fluorophore for silicone. Because silicone has elastic, sealable, and durable properties, many companies such as NASA use silicone as a coating for the machinery. However, due to its clear appearance, manufacturers have a difficult time detecting tears and damages in the coating, leading to possible equipment breakdowns and up to 65% in profit losses. To solve the problem, I investigated HCDs as a possible fluorophore for silicone, so that tears can be found by simply using a UV light. HCDs were used because they are safe, biodegradable, and have high fluorescence. I hypothesized that mixing the HCDs and polydimethylsilicone, PDMS silicone, will make the silicone fluorescent because both are nonpolar, and HCDs will be able to break apart the London dispersion forces in silicone and have interactions, making the silicone fluorescent. The materials used to make the HCDs and PDMS groups are polonic F68, glass vials and pipettes, an analytical balance, water, phosphoric acid, microwave synthesizer, toluene, glass slides, metal molds, oven, UV lights, PDMS silicone base, curing agent, and centrifuge. And for characterization, I used a spectrophotometer, a spectrophotometer, and FTIR. After spending months on testing amounts to synthesize HEDs and mixing them with silicone with around 5 different procedures, each with around 5 trials each, here's the most successful procedure out of all the procedures. A 1:2 ratio of PF68, nanowater, and phosphoric acid was mixed and inserted into a microwave synthesizer for 90 minutes at 150 degrees Celsius. Toluene was added, extracted, centrifuged, and transferred into a vial and placed under a UV light to confirm its fluorescent properties. 5 groups were made. 1 is the control without HEDs, and 4 have varying amounts of HEDs to see which one would yield the best results. They were then mixed with silicone, dropped past onto the metal molds, and placed under a fume hood to evaporate the toluene, and then transferred into an oven. The samples were then removed from the mold to a glass slide and placed under a UV light for comparison. They were then characterized using a spectrophotometer, a spectrophotometer, and FTIR. UV light examination showed that a concentration of 0.5 milliliters to 1 milliliter led to black spotting, but a concentration under 0.5 milliliters led to little to no black spotting but very few HEDs. With a relative comparison using a spectrophotometer, increased HEDs led to a higher absorbance. However, FTIR analysis showed that there was a lack of OH, CH, and CO peaks, demonstrating few HEDs in the sample. Finally, a spectrophotometer indicated that adding silicone actually decreased emission above the 400 nanometer mark. This meant that there was fluorescence in the silicone, but it could not be seen by the human eye. In conclusion, HCDs could not be used as a fluorophore for silicone because of its low yields in HCDs when mixing and possible quenching from the silicone, disrupting emission from the HCDs. The hypothesis was partially correct, though, as HCDs and PDMS did mix homogeneously with one another, showing how they did in fact have interactions. Research questions that came from this experiment include whether using other organic solvents such as hexane results in more HCD yield, and whether we could change the surface of PDMS to be more hydrophilic for water-soluble carbon quantum dots. Further steps include using danzocabendurine instead of HEDs as a fluorophore and using other methods to synthesize HEDs, such as a one-pot soluble thermal process. Thank you so much for listening.